leave it alone. This too, we've been essentially meaning it's particles. When you did the chem balancer program, you counted symbols. These symbols are a representation of an atom. So we've been treating these particles, these coefficients, as meaning particles as we've learned to balance chemical equations and so on. Well, just like we were able to make a connection between particles and the mole is just a counting unit. So if I have a 2 in front of H2O, it means that I have a total of 4 hydrogens. But that 2 can also be interpreted as a mole. So I'm just changing the counting unit, and we did that when we studied the mole chart at the beginning. This 2 can mean I have 2 water molecules, or it can mean I have 2 moles of water. And if I have 2 moles of water, I have 2 moles of water, I have 4 moles of hydrogen if I took it all apart, and 2 moles of oxygen. Okay, same thing here, 2 moles of hydroxide means I have 2 moles of oxygen and 2 moles of hydrogen. Okay, so the coefficients in these chemical reactions can mean both particles and moles. All right, so that's the first thing to realize. And we're ready to get started. So here are my steps for stoichiometry. It's only 4 steps, and there's a 2B. You won't use that till the next lecture. But the first 4 steps we're going to use today. So you're going to start out a stoichiometry problem always with the balanced chemical equation. And because these coefficients, as I just mentioned just now, mean both particles and moles, I am going to use the mole, of course, as my central counting unit. So if any amount that's given to you in the problem needs to be converted into moles. So I always tell students, if you're not in moles, get there. So you may be starting off with 20 grams, or you may be starting off with, later on we'll do other amounts with different conversions. But if you're in grams, then convert to moles. And that's why I needed you to get your mole chart out, because we're going to need to remember how to do that. You need your periodic table in front of you. Won't be using Avogadro's number so much because this is a more practical conversion from grams to moles. This is the new step, okay? What I've just talked about here, we've learned how to balance chemical equations. We know how to go back and forth between moles and other things, but so that's nothing new. But this is the new step, step 3. Use the coefficients in the chemical reaction to obtain a mole ratio, and we are going to do it as 2 over from. Or another way to look at it as question mark, what you're being asked about, over what you were given. So either way, they are equivalent, and that is what we're going to do to compare one thing to another in a chemical equation. Then, if you need to change back out of moles, that's nothing new either. All right, so let's go ahead and get started by doing some examples. So we need to learn how to do that mole ratio. All right, so I have a chemical equation right here. The question is, for the reaction shown, calculate how many moles of ammonia form. So I am going to start off, I want to scroll before I write, when each amount of reactant completely reacts. Looks like I got that twice, so let me get rid of that. All right, maybe we can even get that equation up closer to the question. Nope. All right. So this is where, so we want to know moles of ammonia, okay? So the first thing I'm going to do is make sure my equation is balanced. And I am going to write under ammonia what I'm being asked. So this is my question mark. I want to know how many moles, okay? I am going to give myself a little room right here. And I didn't need as much here. Okay. All right, so question mark moles. So my first amount is 5.3 moles of N2H4. So I am given the amount of one other substance. Now, it does not matter where you're given. It doesn't matter what side you're on, what direction you go in, nothing matters. So this is the deal. If I know the amount of one substance, doesn't matter where it is in this reaction, I can get the other substances using this mole ratio. So I'm already in moles. I have a balanced chemical equation. So I'm ready to move. This is a horizontal step. I tell students, and as we get into the full-fledged where we're using all 4 steps, it's like a box. So you're going from what you're given to moles if you needed to change, then you move to what you're being asked about, and then you go back to whatever amount they are asking. So if you can keep it straight, keep it organized, this is really not that difficult. All right, but so I only have to do one step here. I'm not doing the whole box. I'm only doing the mole to mole step, which is using the mole ratio, the new step. So it is the coefficient. I'm going to take this amount in moles that I was either given or I got there, and I'm going to multiply by the coefficient of what I'm moving to, TO, or where the question mark is, over what I'm coming from, or from what I was given. So 5.3 times 4/3 is going to give me my new amount. And I can compare any two this way. And we're going to do this 4 times. Let me get my calculator. All right, so probably already got yours already figured out. I wasn't ready. All right, so 5.3 times 4 divided by 3. Okay, so I get 7.07 as my, now I'm given 2 significant figures, so we're going to round that to 7.1 moles. Okay, so my very first answer is 7.1 moles of ammonia. All right. All we're going to do for B is change the amount of what we started with, and we're still in moles, 2.28 moles of the N2H4. I'm going to use the same mole ratio, 4/3, because I'm going between the same two things. And I get 3.04 moles for B. Or for 2 significant figures, I guess I had 3 given to me in B, so I can leave that as 3.04 moles. The coefficient of what you're moving to, which is right here, over what you're coming from, which is right here. Okay? In C and D, we are going to be going from nitrogen to ammonia. Okay? So things are going to be a little different. So I'm going to go ahead and erase what is here. Use a slightly smaller eraser. And I'm going to set up my new scenario. Now, with you and paper, that you're actually doing this on paper, you might want to even write your chemical equation again so that you can keep everything organized, so that I can put the amount given under the substance I'm being given, and then I can write my question under the substance I'm being asked about. Now, this is one thing I want you to remember. We are not changing the master recipe, okay? Just because I've changed the amounts. I don't change the coefficients. I've seen students do that. So I'm already in moles, so I need to move to my question mark, which means I will be taking those moles and multiplying by the coefficient in front of the thing I'm moving to, or for the question mark, over what I'm coming from, which in this case is the nitrogen, and it has a 1 in front of it. So 5.8 times 10 to the minus 2. I got 0.232 moles for my answer to C. Two significant figures, so we'll leave it as 0.23 moles of ammonia. All right, same thing in D, 7.76 times 10 to the 7th looks like moles of nitrogen, and I'm going to move to the same, so we've got the same mole ratio going on here, so times 4 over 1. And I'm going to have to get a different calculator. I was using my phone. All right, so 7.76 times 10 to the 7th. That's a lot of, divided by, I'm sorry, times 4. And I get 3.1, 3.10 times 10 to the 8th is what I got for D. And I can take it out, 3.10 times 10 to the 8th. I'm going to check that one more time. Yep, that's what I got. So 3.10 times 10 to the 8th moles. Remember, now that we've gotten back to using the calculator again, never write a number down without putting the unit after it, especially when you're doing these kinds of calculations, because your attention gets diverted and you look back at the number you wrote down and you really have no idea what it's for. And another reason to keep it neatly organized in terms of your information as it relates to the chemical equation is you know where you are. All right? All right, so that's the new step, the mole to mole step. All right, for the reaction shown, calculate how many moles of each product form when the given amount of each reactant completely reacts. And then they have this statement of assume there's more than enough of the other reactant, so don't worry about that. Has to do with limiting reactants, and we'll deal with that in the next lecture. All right, so A, for how many moles of each product is my question. So let me go ahead and put that in. So question mark moles, question mark moles. All right. I am going to start with in A with 4.6 moles of the C3H8. All right. So I am going to 4.6, right? I'm already in moles. I have a balanced chemical equation. So I'm ready to move to my first question mark. So this time it'll be times what I'm moving to, which is 3, over what I'm coming from, which is 1. So 4.6 times 3. Change calculators. I hate that calculator. 4.6 times 3. And I end up with 13.8 moles for my first product. Now, in order to answer this second question for the water, I can either come back to the C3H8 and do all the way across, or I can go right from the CO2. I will get the same answer no matter which one I use, and I will prove that to you. So I'm going to go back to the C3H8 and use my 4.6 moles, and then move to the water. So it'll be times 4 over 1, okay? So 4.6 times 4, I get 18.4. 18.4 moles, all right, of water. But if I went from the CO2, I would take my 13.8 times 4 over 3, and I get 18.4. So it doesn't matter. That's the beauty of stoichiometry. These coefficients are giving you the proportions related to one another. So I can use any two. I can go in any direction. It doesn't matter. Okay? That is A. Now let's do B. I have to erase. Okay, and this time I'm going from oxygen, so 4.6 moles of oxygen. Okay, how many moles of each product? So in these first two examples, we are really honing in on that new step, the mole to mole step, the mole ratio, using the mole ratio. This is the only step in which you use the coefficients. All right, so I'm going to take my moles, I'm already in moles, and I'm going to use my coefficients times 3 over 5. I am moving 2 carbon dioxide from oxygen. So 4.6 times 3 divided by 5, and I end up with 2.76 moles of CO2. Okay, I'm just going to go right next door because it's easier, times 4 over 3. And the best thing to do when you're doing these stoichiometry problems is just don't clear your calculator, because chances are the next number you're going to be working with is the one you just finished getting in your calculator. All right, so there are my moles of CO2 and my moles of water. In this second, to get the water, I was moving from the CO2, so that's why its coefficient is on the bottom. I was moving to the water, and that's why its coefficient is on the top, 2 over from. All right, I'm going to erase and do C. All right, so we're going back to the C3H8, and we're going to put in a different amount this time, 10 to the minus 2 moles. Question is still the same. Okay, so I'm already a mole, so I can move, times 3 over 1 for the carbon dioxide, and I get 0.167 for the carbon dioxide moles, and then times 4 over 3 to get the water, and I get 0.223 moles. Right, and that is C. We're going to use exactly the same number of moles of oxygen in our last step. Okay, so one more time, 5.58 times 10 to the minus 2 moles of oxygen. We're going to move to CO2 and water again, times 3 over 5, because I'm moving to the carbon dioxide from the oxygen, .033, 0.033, or 3.3 times 10 to the minus 2. It's actually 335. So if I do put it in scientific notation, I can get a little more accuracy out of it, as I can use 3 significant figures. So that many moles of carbon dioxide, and then moving to the water, see that number is in my calculator, times 4/3 to go to the water, going to water, so that's why the 4 is on top, coming from the carbon dioxide, that's why the 3 is on the bottom. So times 4 divided by 3, and I end up with 4.46 times 10 to the minus 2 moles of water. And that is 2 multi-part problems where we are honing in on that new step, which makes it stoichiometry. All right, let's see. All right, we've got 2 more, and we're going to probably do a little bit more on these 2 rather than just that one step. First of all, in number 3, we've got to balance this equation. All right, so at any time, stop the video and give this a try on your own. So we're going to put a 2 there for the aluminum. 3 sulfates. I need a 3 here and a 3 here. Okay. What kind of reaction is this? This is a single replacement reaction, and we will be honing in on those in the exam 4 material, actually. You can write ionic equations for these as well, but everything won't cancel because aluminum is a solid here and it's a 3+ over here, so remember that. All right, we've balanced our equations. How many moles of sulfuric acid, so before I go any further, I'm going to write down my question, are required to completely react with 8.9 grams of aluminum? All right, so you see that the 2 things we're working with are on the same side. That's okay. All right, I have a balanced chemical equation. I've written down my info. If you're not in moles, get there, and I'm not in moles, so I am going to do what I call a vertical step in this box, okay? And I know how to go from grams to moles. I know I need a periodic table. All right, so I am going to grab mine, and I'm going to ask you to try to remember how you go between grams and moles. Get your mole charts out. All right, I've got my periodic table. Now, when I'm doing stoichiometry problems, I like to write my molar masses, and that's what I'm going to be needing, above the species that I'm working with. That way, if I need to go back and redo anything, I don't have to look it up again. Okay, so aluminum is 26.98. Now, when you're doing this mole of grams to moles step, we're not using the coefficients. We didn't use them before when we first learned how to do this, and the only time we use the coefficients is when we're moving. So I'm going to write it right here. I'm going to take 8.9 grams of aluminum, and I'm going to remember with my units that I need to divide by the molar mass in order to get those grams to cancel out. So 8.9 divided by the 26.98. And I end up with 0.33 moles. Now, you can write that down on your paper, but I'm leaving in my calculator 0.32987. I'm not clearing it, okay, so I won't lose any accuracy. Now I have my moles. I can move to my question mark by multiplying times the mole ratio of what I'm moving to over what I'm coming from. So that number's right there in my calculator, times 3 divided by 2, and my answer is 0.495, which is a few too many significant figures, so we'll call it 0.50 moles. Okay, so that was moles. When I move using the coefficients, I am still in moles. All right? And that is B. C, how many grams of hydrogen are formed by the complete reaction of 0.341 moles of aluminum. I have a new scenario. This is common with stoichiometry problems. So I really need to erase what I have so that I can put my new information underneath. Okay. All right, so I've already put my question mark, and I'm starting with 0.341 moles of aluminum. Now in the previous problem, I had to get into moles, I moved, and then I stopped. So I did this much of the box. We're doing half a box still in this one because I am already in moles, so I'm going to be able to move, and then I'm going to convert back to grams. Okay, so I'm in moles, so now I can move to my question, times 3, the what I'm moving to over what I'm coming from. So 0.341 times 3 divided by 2, and I get 0.512 moles, 0.512 moles. So you're not quite finished yet. 2 H's, if I take the molar mass on the periodic table and multiply times 2, because of the little 2, I get 2.016. So 2.016 or 2.02 is the molar mass times 2.016 grams per mole, and the moles cancel. Times 0.512, and my answer is 1.03 grams when I multiply these two. So let me make that clearer by erasing some of this, and that is equal to 1.03 grams. Now, what I'd like to show you before I move to the next problem, because we're doing pretty well with time, I would like to show you how in this last example, how we could have done that all in one conversion, not a conversion step, but using dimensional analysis, I can do the same thing I've just shown you. Now, I like the visual of the box, but let me show you what I'm talking about. Okay, I'm starting with 0.341 moles of aluminum. All right, I need to get to moles of hydrogen. There are, erased my balancing too. Let's see, there's a 2 here, there was a 3 here, and there was a 3 here. 6, yes. Okay, so times. So I'm in moles of aluminum, I need to get to moles of hydrogen. So there are 3 moles of hydrogen. What I want on top for every 2 moles of aluminum. And that cancels. And then I want to get to grams of hydrogen, so I use that molar mass, the 2.016, 2.016 grams per mole of hydrogen. And then it tells me what to do. So 0.341 times 3 divided by 2 times that to get our final answer, which was 1.03 grams. All right, so get into moles, move using the coefficients. The other conversions are the mole chart. Okay, scrolling to our last problem here, and it's a multi-step problem, so, whoops, wait. There we go. All right, so I've got an equation here. Is it balanced? Looks like it is. What minimum mass of hydrochloric acid in grams would dissolve a 2.8 gram iron bar on a padlock? So I am doing the whole box because I am not into moles, so I am going to have to get there. And then I will move, and then I have to convert back to grams. All right, so I will do that up here, and then we'll show you how to do it with dimensional analysis. Now I am going to need the molar mass of both of these substances, so I'm going to go ahead and write those above each, so that makes it nice and easy. right? I am going to need those. In my first step, I'm going to be converting to moles of iron because that's what I'm giving. You always start with the number you're given. So 2.8, so I'm going to do that down here as well. So 2.8 grams of iron times 1 mole of iron has 55.85 grams. Okay, so that is my first step. So if I do that and stop, I end up with 0.05 moles. Okay, so now I am in moles. I got there, and now I can move by using the mole ratio of what I'm moving to over what I'm coming from. That has a 1 in front of it. Okay, and I get 0.1 moles. So dimensional analysis, this is what I'm doing. I am in moles of iron at the moment, but I want moles of HCl, so that goes on top. 2 moles of HCl for every 1 mole of iron, and I am officially out of iron. I've moved away from iron, just like my diagram up here shows, because now I am under the HCl. But I want grams of HCl, so I have one more step, and that is to multiply by the molar mass, which is always in the units of grams per mole, and the moles cancel, and I will end up with my grams. So times 36.46, 0.1 times 36.46, so I should end up with 3.65 grams as my final answer. Okay, it's really quite simple. Balanced chemical equation. Write the info you are given in the problem under those species. Get into moles. Move using the mole ratio of 2 over from. That is the only time you use the coefficients. Only step for coefficients. Okay, then I will convert back to whatever I'm being asked for out of moles. Sometimes you stop at moles. All right, let's see if there's any more to this. How much hydrogen would be produced by the complete reaction of the iron bar? So how much usually means grams, so I'm just going to put that in. And luckily I still have, it was 0.1 moles of this, and it was 0.05 moles of this. So I can use either one. I have to go back to moles in order to move over to the hydrogen. So I'm just going to go ahead and use the HCl. That's okay, won't make any difference. Hydrogen has a 1 in front of it, the thing I'm moving to. HCl, what I'm coming from, has a 2. So I end up with 0.05 moles of hydrogen. But look, hydrogen and iron have the same coefficient, so they're going to have the same moles. And then all I have to do is convert back to grams. The molar mass here is 2.016. So times 2.016 grams per mole. And I get 0.1008. And my significant figures is really 2. So I guess it's 0.1 grams, 0.10. Right? And that is stoichiometry. We are going to continue on with our stoichiometry discussion in this lecture. We're going to add the concept of limiting reactants, which can be explained by many different analogies. But let's just talk just for a moment in review about what we talked about in the last lecture. And that is if we have a chemical reaction, the coefficients in front of the products and reactants can help us to determine amounts given one amount. So it's a proportion, it's a recipe. You never change the coefficients once you've written your balanced chemical equation, and that's your first step in a stoichiometry problem. In the problems that we did last time, we would start with first of all, we started off with amounts in moles. And then the second step is, if you're not in moles, get there, because these coefficients also mean, in addition to particles, they mean moles. So it's 1 mole of A plus 2 moles of B to give 3 moles of C and 4 moles of D. If I want to know how much C am I going to make if I start off with 2 moles of A, and I'm being careful in placing my amounts underneath the species or the substances that I'm being given information about, and the one that I'm being asked a question about. So I'm already in moles, so the only time I use the coefficient is in this moving step. As I go from one to another, and it doesn't matter direction, I can be on the same side, doesn't matter. I'm always going to take that amount in moles and multiply times the coefficient of what I'm moving to over what I'm coming from. So I will make 6 moles of C. If I wanted to know how many moles of D, I can either go from C or from A. I'll get the same answer. Showed you that in the last lecture. I'm going to go from C since it's close by. I will take those 6 moles of C times the coefficient of what I'm moving to, the 4, over what I'm coming from, which is the 3. And 6 times 4 is 24 divided by 3. 8 moles of D are made. Now, the only difference in the type of problem that you might see is if you are not given amounts in moles and you are asked for an amount that's not in moles at the end. I explained in the last lecture that I always think about these problems in terms of the setup as a box. So if I were given 4 grams of B is what I'm starting with, and I want to know how many grams of D I'm going to make, well, my first step is to get into moles. And I am going to use the periodic table to do that using our old mole chart. 4 grams times, I'm going to be dividing by the molar mass from the periodic table, okay, for whatever B is, to get into moles. Then I will use the coefficients. In this case, it would be times 4 over 2, okay, and I would have my moles of D, and then I would do another periodic table step. So here's the box, okay, box, where I then take those moles of D and use the mass from the periodic table to switch it back to grams. I do not use the coefficients on these vertical steps, okay? We didn't before. That's a mole chart step. The only one I'm using the coefficients on is the horizontal step, the moving step. And that is the basics of stoichiometry. The only thing that's going to change with what we're going to talk about today is often we have a limiting reactant situation. So let's talk about my analogy there, and then I will use this same example to pretty much chart out. It's one additional step, and that is step 2B on the steps provided in the last lecture. So I've used many different analogies. This one is cars. If I have 8 car bodies and 48 tires, how many cars am I going to make? Well, I think we can talk about it in terms of an equation. That's what we would do if it were chemistry. So 1 car body, if we do this systematically, plus 4 tires equals a car. Okay. Well, if I have 8 car bodies, how many tires am I going to need? I know you can do this in your head, but this is how we're going to do it, as a chemistry problem. Well, 8 times 4 over 1, right? I'm moving from car bodies to tires to figure out how many tires I need, and 8 times 4 is 32, okay? So 32, 4 over 1, 32 tires. So I have 16 tires left over. Now, it's as easy to conceptualize with tires and car bodies, but if I were doing it the chemistry way, we haven't done that entirely yet. This is what I would do. I would take let me erase my amounts here. Well, I left the 8 there. I will take the 8 and the 48 as my amounts. I will divide the 8 by its coefficient. So I urge students not to write that number down because you're not going to use the number you get when you divide by the coefficient. It just tells you which one is smallest. Okay? In the case of this example here, car bodies is limiting. We already know that. I cannot make more cars because I don't have enough car bodies. I've got plenty of tires. So we call this the excess. Okay? Well, the way that you do it when it's not so obvious is you take the amount in moles, of course. So that's why this is step 2b. 8 divided by 1 versus 48 divided by 4. 48 divided by 4 is 12. 8 divided by 1 is a smaller number. That tells me this is the limiting reactant. You must use the limiting reactant or you will be promising somebody more cars than you can make. If you are given in chemistry, using this example that I have written up here at the top, if you're given in moles, then it's easy. You're already there. You can divide by the coefficient. So if I have 2 moles of A and 4 moles of B, 2 divided by 1 versus 4 divided by 2 is actually the same number. This is the exact stoichiometric ratio I need. So there is no limiting reactant, okay? Because I got the same number when I divided by the coefficients. So let's change it. Let's say I have, let me just erase, okay? So this is the new step. Divide by the coefficient after you're in moles, and that tells you which one is limiting. And then you go from there and everything's the same. For those of you who are wondering how it all works. So if I have, let's make it big. Let's say I have 16 moles of A and 46 moles of B. All right? 16 divided by 1 versus 46 divided by 2. 46 divided by 2 is 23. A is limiting reactant. I must use A to figure out anything concerned with products. I used to, when I taught high school, I used to make it s'mores day when we talked about limiting reactants. And I would tell the students to bring in, they would have to organize it, the graham crackers, the chocolate, and the marshmallows. Well, I knew they wouldn't get the proportion right. And I knew they'd probably forget, so I usually backed them up with some supplies. But I, get to teenagers with food every time, and I would drive, home the idea of proportion, this limiting reactant. So most of the time, it was usually chocolate that was limiting, and then we'd have tons of marshmallows and maybe graham crackers left over. All right, so here's a little problem here, and it is before reaction started, after reaction is completed. So we could, looks like we are taking one of the open ones and one of the closed ones. We could count. We're not going to do that. This picture is just to drive home the fact that when this is completed, I see all of the open circles have been used up. Therefore, it is the limiting reactant. I see lots of these dark circles, I'm sorry, not that one, that left over, so it is the excess. Now, there, if you look, I'm going to click on these two links here in a moment. If you look in your book, and I know there's a lot of students who are, who do rely on that textbook, they're going to show you the long way. They're going to take the amounts, they'll switch them into moles, they'll essentially do the whole problem twice, okay, to figure out which one gives you the smaller amount of product, and that's how they do limiting reactants. My way works every time, and it's so much shorter. Divide the moles by the coefficients. That tells you which one is smallest. Don't use the number you get when you divide. All right, let's go back to these links, and let's click on, I can't remember what they're for. Oh, that's just for the diagram, so back to the notes. I try to reference my diagrams. This is a flash, though. Let's do that one.
Nitric oxide, NO, is produced when atmospheric nitrogen and oxygen react at high temperatures in an automobile engine. Once released into the atmosphere, nitric oxide is quickly oxidized to nitrogen dioxide, NO2. Nitrogen dioxide is a toxic brown gas. Much of the brown haze present in photochemical smog is due to the presence of nitrogen dioxide. The left side of the two-bulb vessel contains nitric oxide gas, NO, and the right side contains oxygen gas, O2. Click on one of the buttons to choose the number of molecules of NO you would like to react with the number of molecules of O2.
All right, so we have 3 different scenarios here, and we're going to go through them. And because I like these visual animations, I think they're helpful. Oops.
Nitric oxide and oxygen gas are reacted in a 1-to-1 mole ratio. There are 4 molecules of NO in the left bulb and 4 molecules of O2 in the right bulb. The valve separating the bulbs is opened, allowing the gases to mix. The reaction occurring is 2NO plus O2 producing 2NO2. 4 molecules of NO are reacting with 4 molecules of O2. The 4 NO molecules require only 2 O2 molecules for reaction. Note the 2-to-1 mole ratio in the balanced equation. Therefore, 2 O2 molecules remain after reaction. The reaction stops once the nitric oxide gas runs out. NO limits the amount of product that can be formed and is therefore called a limiting reagent. Oxygen gas is present in excess.
Okay, what I'd like to do here is go through these amounts, these different amounts, and we're going to predict how much NO2 are we going to make. We're also going to predict how much of the excess is left over, and that is a step that really confuses students. So first thing we're going to do is determine the limiting reactant in each scenario, and I'm going to start with this one that's just done, even though you've seen it happen. We are going to then determine the amount of NO2, how many NO2 molecules. Now remember, those coefficients mean molecules and moles. In this case, we're going to use them as molecules. Wouldn't be any different if you were in moles. And then 3, how much excess is left over. Okay, so we're going to go through that with this very simple example. You'll see what happens as I click on each one, and hopefully the process will be clear to you. All right, so in this first example, we had 4 NOs and we had 4 O2s. Using the steps that I've given you, 4 divided by 2, we would get into moles first. That's why it's step 2B when you have a limiting reactant. How do you know you have a limiting reactant problem? Limiting reactant problems are evident from having amounts for 2 or more reactants. Then you have to figure out which one am I going to use. Okay, so that's how you know you have a limiting reactant problem. All right, now, this is what this is all about, this animation. Okay, so I'm in moles, or in this case, I've counted molecules, same difference. 4 divided by 2 is 2. 4 divided by 1 is 4. This is a smaller number. This makes it the limiting reactant, okay? Now, I don't use that number that I got when I divided. In fact, I don't even like to write it down. Now, when you get to some of the problems, you might have to write it down, but write it down small and off to the side. Okay, now I'm going to determine how many NO2s using our same old process. Taking that amount in molecules this time, but you'd be in moles normally. 4 times coefficient of what I'm moving to, 2, over what I'm coming from, 2, and that's why we made 4 molecules of NO2. Okay? All right, now how much of the excess is left over? This step always confuses students. Go back to limiting reactant. It determines everything. Okay, so you're going to go back to here, and we're going to move to the excess. 4 times 1 over 2 tells me how many, use mole ratio to determine amount used, Okay, so 4 divided by 2 is 2. I used 2 molecules of O2. Subtract to get how much is left over. In this case, it's 4 minus 2 equals 2 molecules left over. Or if you're in moles, you'll be doing in moles. Okay, left over. All right, so we're going to do this step 3 more times with these other 2, and then we'll check them after we've done our 1, 2, 3. Okay? All right, so let me erase this right here, okay, to do the next scenario, and then we'll click on it and see, if we see it in action. Okay. All right, so new scenario. All right, 6 molecules of NO, 3 molecules of O2. 6 divided by 2 is 3. 3 divided by 1 is 3. So I've got the exact stoichiometric ratio. Neither one is limiting because I get exactly the same number. You see, this is 2 to 1, so 6 is 2 times 3. So it doesn't matter which one I use, I will always figure out the same, I'll always get the same amount of the product in this case. So 3 times 2 over 1, I will make 6 molecules of NO2, and I will have nothing left over of either one because I don't have a limiting reactant or an excess. So let's click on the button and see if we are indeed correct.
Nitric oxide and oxygen gas are reacted in a 2 to 1 mole ratio. There are 6 molecules of NO in the left bulb and 3 molecules of O2 in the right bulb. The valve separating the bulbs is opened, allowing the gases to mix. The reaction occurring is 2NO plus O2, producing 2NO2. 6 molecules of NO are reacting with 3 molecules of O2. They are reacting in a 2 to 1 mole ratio as represented in the balanced equation. No reactants remain after the complete reaction.
Right? Let's go ahead and do this last one. 6 molecules of NO, 2 molecules of O2. 6 divided by 2 is, now if we were in a real problem, we'd have to make sure we were in moles. 6 divided by 2 is 3. 2 divided by 1 is 2. This is the smaller. This is my limiting reactant. All right, so we've done step 1. Step 2, how many molecules of the product have to use a limiting reactant times 2 over 1. 4, I will make 4 NO2s, okay? How much of the excess is left over? Go back to the limiting reactant, move to the excess using the mole ratio, times 2 over 1. That tells me how many I use. I use 4, okay, because 2 times 2 is 4. I subtract to get the amount left over. All right, so I should have 2 molecules of NO left over, use up all the O2s, make 4 NO2s.
Nitric oxide and oxygen gas are reacted in a 3 to 1 mole ratio. There are 6 molecules of NO in the left bulb and 2 molecules of O2 in the right bulb. The valve separating the bulbs is opened, allowing the gases to mix. The reaction occurring is 2NO plus O2, producing 2NO2. 2 molecules of O2 are reacting with 6 molecules of NO. The 2 molecules of O2 only require 4 molecules of NO for reaction. Note the 1 to 2 mole ratio in the balanced equation. Therefore, 2 NO molecules remain after the reaction. The reaction stops once the oxygen gas runs out. O2 limits the amount of product that can be formed and is therefore called the limiting reagent. Nitric oxide is present in excess.
All right, so there are 2 NOs left over. We made 4 NO2s. All right, the process is really pretty simple. Get both your reactants, or you have 3, get all of them in moles, divide by the coefficient to figure out which one is limiting, and then use it to figure out everything else in the problem, including how much of the excess is left over. You use the limiting reactant to figure out how much of the excess you use, and then subtract. Okay, I think that's a lot easier than doing this. All right, so let's do some problems from the notes. For the reaction shown, find the limiting reactant for each of the initial quantities of reactants. So I'm going to put in a little, little space here so I can write underneath. Okay. And now we are going, now all of these are in moles, so that makes it nice and easy. So 1 mole of chromium for A, 1 mole of oxygen. Okay. 1 divided by 4 versus 1 divided by 3. I'm in moles, so I can go ahead and do this step 2b. So 1 divided by 4 is the limiting reactant for A. Okay. So what I'm going to do is identify those by putting that over, and then I will erase, okay, to do the next one. All right. All right, B, 4 moles of chromium and 2.5 moles of oxygen. 4 divided by 4 is 1. 2.5 divided by 3 is going to be smaller than 1. So this is my limiting reactant. Okay, so oxygen is limiting in B. Okay, so I don't even have to go through the math. I mean, for some of it, I can just know which one is smaller. All right. C, we have 12 moles of chromium and 10 moles of oxygen. 12 divided by 4 is 3. 10 divided by 3 is 3.33 something. 3333. So chromium is the limiting reactant in C. All right. And then our last one, 14.8 moles of chromium and 10.3 moles of oxygen. Can I do this without a calculator? No. All right, so 14.8 divided by 3, 4, is 3.7. So I hate to write it down because I won't use it. That's why I don't like writing it down. 3 points, oh, no. So 3.7, okay. And 10.3 divided by 3 is 3.4. So this is my limiting reactant, this one, okay? So I'm going to erase those numbers because I don't want to mess up and use them, because I'm still going to use the 10.3 to do any other question in the problem, okay? All right, I want to scroll a little bit and get rid of all that. All right, next one. Why don't you pause the video and try this on your own, because actually I don't need the spaces here. I need them underneath the equation. Okay, I think what you will have seen when you print the notes out this time is that after I've done the video, I copy and paste the document back into the notes so that the spaces are there in the right places. So hopefully that has helped you. Okay, 2 moles of titanium and then 2 moles of chlorine. Okay, so 2 divided by 1 versus 2 divided by 2 is 2 divided by 1 is 2. 2 divided by 2 is 1. So this is my limiting reactant in A. Okay. B, 5 moles of titanium versus 9 moles of chlorine. 5 divided by 1 is 5. 9 divided by 2 is 4.5. So chlorine again is the limiting reactant. I would use the 9. .483. This is more like the kind of numbers you're going to get in a problem. 0.911. 0.483 divided by 1 is a larger number than 0.911 divided by 2. This is going to be like 0.45 something. So this is again my limiting reactant. Then one more, and this is true to form for your textbook. This last one will switch it up, and titanium will be the limiting reactant. So 12.4 moles for the D, 15.8 moles for D, and no, for chlorine, and no, they did not switch it up. 12.4 divided by 1 is larger than 15.8 divided by 2. Chlorine, again, is the limiting reactant. Okay, so all we're doing there is we had a balanced chemical equation. Our amounts were in moles. We were dividing by the coefficients to determine the limiting reactant. The problem from there on is the same as what we've done in the previous lecture. Right, so here's a real limiting reactant problem where you were not given amounts in moles. All right, so let's write down what we have. We have 42.9 grams of this, and we have 6.86 grams of this, and they want to know how many grams of HF will be produced. So the first thing you've got to do is get both of these into moles. All right, so periodic tables at the ready. All right, so we have got to add up our molar masses from the periodic table, so that's what I'm going to do. Right now, I am going to be writing those on top of the subspecies, the substances in the equation. So I'll be writing the molar masses on top. That way, if I make a mistake, I can always go back. Now I know that this is 18.02, so I'll go ahead and put that one up there. And then let me go ahead and add up the others. Do that one again. Okay, I get 62.05 for the molar mass of the CH3COF, 62.05. All right, and then HF will be 19.01. All right, so all I've done is add up the masses from the periodic table. This equation is balanced. Yes, two H's. Okay, so now take your 42.9. This is a mole chart step divided by that 62.0. I can't even read my own handwriting. 702. 0.691 moles is what I got for this one. Okay, 6.86 divided by 18.02. And I get 0.381 moles of, okay, the H2O. All right, this divided by 1 versus this divided by 1. Obviously, this is my limiting reactant and is the one I must use. I am now in moles, and so everything from this point on is the same. So it's the complete box times 1 over 1. So I have the same moles of the HF, and now I'm under HF, so this is what I'm going to use its molar mass to convert back to grams. And that's not 19.01. Yes, it's 20.01. All right, so I messed up there. 20.01 for the hydrogen and the fluorine. So let me do that one more time. And that is 7.26 grams of HF. All right, get them into moles, divide by the coefficients to see which one is limiting. From there, it's pretty much the same. We only have one thing to add to today's lecture, and that is percent yield. One more problem before we get into percentage yield. Okay, so 29.4 grams of hydrogen were reacted with 740 grams of chlorine. How many grams of HCl will be produced? Okay, convert them both to moles. And I'm going to need molar masses for everything. So this is I'm going to go with 2.02, 70.9 for chlorine, and 36.46 for HCl, because I'll need that later. All right, so 29.4 divided by the 2.02. And I get 14.55 moles. Okay, 740 divided by 70.9, and I get 10.44 moles of the chlorine. Really looked like it was going to be the hydrogen, didn't it? But it's not. The limiting reactant is the chlorine. Okay, so I'm going to use it. This is the limiting reactant. I'm going to use it to figure out my HCl. 2/1 is my mole ratio. So 10.44 times 2. And I end up with 20.87 moles of HCl. And then there's my molar mass times the 36.46 grams per mole from the periodic table to convert back to grams. And I get 761.1 significant figures. I'm going to go with 3 significant figures is good, so 761 grams of HCl. Okay. All right, last thing to talk about in this lecture is percentage yield. And it is a step that actually happens at the end. So we've just introduced a little sub-step at the beginning, step 2b, and step percentage yield is just, you do that after you've done the problem. Before I leave this, let me just say that what we have just calculated and what we have done every time we have calculated a problem so far is we have gotten what is called the theoretical yield. That is the yield on paper that if everything were perfect, that's what you would get. Okay? Well, the world is not perfect, and you often get something different. And we call that the actual yield, what you actually get in the laboratory. So percentages are always part over the whole, so it's what you actually get in the lab. Usually it's less than the theoretical, it's not always. So actual over theoretical times 100. Now, you will either be given this in the problem or you will be given the percentage yield. You are never given the theoretical yield. You are expected to do the stoichiometry problem. Okay? So you always have to do that. So that's nothing different. You're going to do exactly the same thing we've been doing. But then at the end, you'll calculate a percentage yield. All right? Okay, so here's a problem. 63.1 grams of HCl reacts with 17.2 grams of oxygen. 49.3 grams of chlorine are collected. So this right here, you being given something about a product and then being asked about a percentage yield means that what they gave you in terms of the product is the actual yield. And you will not use that till the end. One thing I did not mention above is percentage yields are about products, about making products. Okay, so if you were given an amount of a product, then that means you've been given the actual yield. And they're asking you here to determine the percentage yield after you found the limiting reactant and the theoretical. Okay, so this is how this second sentence here with the stars, how it's actually worded in your textbook. Determine the limiting reactant, which you would do first, because you have been given amounts for 2 reactants, convert them both to moles. You then have to do the theoretical yield, and then you can get the percentage yield using this actual yield you've been given. However, I just want to point out that an alternative way of asking the same question is, what is the percentage yield for this reaction? So they're being nice in leading you to, to doing this limiting reactant part first, then do the theoretical, and then do the percentage. They didn't have to do that. And you may see questions where they leave that out. It is assumed you know to find a limiting reactant. What you were given regarding chlorine is the actual blah, blah, blah. So Again, how do I know I have a limiting reactant? When I am given amounts like this for two or more reactants. Convert them to moles. If you're not in moles, get there. And then I will determine the amount of chlorine. How did I know it was chlorine? Because I was given information about chlorine. This is going to be my theoretical. And you have to do this every time. And then at the end, we'll combine these two to get the percentage yield. Okay? So HCl, periodic table, 36.46, 32 for oxygen. So 63.1 divided by 36.46 moles of HCl are 1.73. Okay, 17.2 divided by 32.538 moles of oxygen. 0.538 divided by 1. Is that a smaller number than 1.73 divided by 4? 0.4, when I divide by 4, I get 0.433 here for HCl. Don't want to write it down because I'm not going to use that number. This is my limiting reactant. I get a smaller number when I take the amount in moles divided by its coefficient versus this one. All right, so I have to use this to calculate the grams. Now I'm already in moles times the coefficient of what I'm moving to over what I'm coming from. So 1.73 divided by 2 is 0.88 moles. Now on a multiple choice test, 0.88 grams would probably be one of the answers. Well, it's a percentage yield, so maybe not. Okay, so 0.88 moles and 70.9 was my molar mass for Cl2. So 0.88 moles times 70.9, 62.39 grams is my theoretical yield. At any point, if you don't understand how I got the numbers, stop the video, try it yourself, okay? Back up, go through it again, all right, to make sure that you understand where all of the numbers come from, all right? So percentage yield is actual over theoretical times 100. So 49.3 over 62.39 times 100, and that's our percentage yield. And I get 79.01 or 79%. Okay. Scrolling, which means I will lose that. All right, we've got two, and then two more problems to make sure we understand this process. All right, so 27.5 grams of N2H4. I mean, before I even read the problem and get that deer, and you know, this goes for you, get that deer caught in the headlights look, I'm writing down the information as I read it. Calculate the masses of all reactants and products. So that means you're going to find out how much of the excess is left over once the reactants have reacted as much as, hold on, I'm going to lose that, darn it, as possible. Okay, so I have to figure out my limiting reactant. Now this is not a percentage yield question per se, but we do need to have, there we go, yay, to have practice with that whole excess thing. So convert them both to moles so I can figure out my limiting reactant. I will use the limiting reactant to answer these questions, and then I'll figure out how much of the excess is left over. All right, so N2H4, 32.04 into O4, 92, 18.02, and 28. Just writing all my molar masses on top. So 27.5 divided by 32.04, and I get 0.858 moles. Okay. 74.9 divided by 92, and I get 8.814. All right, so 0.814 divided by 1 versus 0.858 divided by 2. This is my limiting reactant, and I must use it to figure everything out. So let's go ahead and do the excess first since it's right there. So go to your limiting reactant, move using the mole ratio, 1 over 2. What I'm moving to, 1 divided by 2. 0.429 is how much I'm using. This is when I do this, I get how much I'm using. I automatically put in subtract because I'm going to subtract that from my original amount. And I get 0.385 moles left over. And if I want to put that in grams, I go ahead and just multiply times the 92. See how nice having it there up top. I needed it again. And I get 35.42 grams left over. Okay. Figuring out my products, I have to use the limiting reactant. All right. So 0.858, I'm going to do it down here. 0.858 moles times 4 over 2. Okay. To get your amount of H2O. And I get 1.716 moles, and then times the 18.02 to get my grams, okay? So 30.92 grams of water is my amount of the water. Now I can use these moles here. I've used the limiting reactant, so I can just use the water to get the nitrogen. So times 3 over 4. And I get 1.287 moles of the nitrogen, and then times the 28 grams per mole. Okay. I end up with 36.04 grams of the nitrogen. Okay. That's pretty much as complicated as it gets. All right, one more, and we're done with this lecture. All right. For the balanced equation shown below, if the reaction of 19.8 grams of sodium produces a 55.9% yield, going to save that to the end, how many grams of Na2O are produced? Now, what they are asking you here is not what the theoretical yield is. They are asking you for the actual yield, okay? But you're given the percentage, so we'll be able to figure that out. First thing you got to do is get the theoretical. Convert this to moles. All right, sodium is 23, and I'll be doing this over here, so that weighs 62. Okay, 19.8 divided by the 23, and I get 0.861 moles. All right, of the sodium. This is not a limiting reactant problem. It's just a percentage yield. Move to the question, times 2 over 4, so dividing by 2, and I get 0.430 moles of the sodium oxide. Okay, and then times the 62 grams per mole. All right, and I get 26.69 grams of the sodium oxide. This is my theoretical. Okay, so 55.9 equals X over 26.69 times 100. Bringing the 100 over, dividing both sides, I end up with, I'm going to move over here to the left, 0.559 equals x over 26.69. Cross multiply and divide. Okay, so times 0.559. 14.92 is my actual yield. Okay, now some of you smarties out there may have realized that if this is the maximum amount you can make, all you have to do is multiply it times the percentage in decimal form. And that's really all you have to do.